So in this last video of our semester, we finally ready to understand a bit more, elaborate the structure of BCH and the Goppa codes a bit more. And for the BCH setting, let me remind you the setting which comes from the rational function fields with the constant field fq to the m. Here fq to the m denotes the field extension of degree m over fq. And for these n distinct rational places in our setting, we consider a subgroup of the multiplicative group of this finite field of order n, particularly which is generated by a primitive nth root of unity beta. And since obviously each beta is the powers of beta is distinct from each other from when I runs through from 1 to n, these places are pairwise distinct. And we denote their sum is d beta, because just to mention that this is determined by this primitive nth root of unity. And for the choice of the divisor g, recall that first we consider the zero and pole divisor of the transcendental x, and we set our divisor g is integer combination of these two divisors, where the sum of these integers run through from 0 to n minus 2. So the degree of g is lies in this branch. And with this particular setting, we define the BCH code as the subfield subcode of the dual code of the ZG code. And now we can write that indeed this dual can be described in terms of the local components of a Weyl differential. Moreover, indeed, it can be described as its dual can be described as in terms of another AG code with divisor H and this is going to be G minus dB infinity. G minus d beta, where omega is particularly determined by a function y. In this case, it's going to be x to the minus n, and where h of x denotes the product of these linear factors. So since this is an nth root of unity, this is going to be x to the n minus 1, and simply the derivative will be n times x to the n minus 1. So more explicitly, this h will be written the divisor of y. So this is x to the minus n plus divisor the derivative of h prime minus h of x minus 2p infinity minus d beta minus g, so that means AP0 plus BP infinity. And if we write the conclusions and this, if we use these equalities, we can see that this divisor again can be described in terms of the divisor P0 and P infinity, and indeed there's these integer coefficients. And thanks to the minimum bound of this AG code, indeed, and the relation between the minimum distance of a code C and its subfield subcode, we are able to give a minimum distance bound for a BCH code. For this exercise description, we saved it, how this look like, how this minimum distance look like in discussion session. And finally, for the Goppa codes, a bit more general setting, instead of considering in a cyclic group of order n of the multiplicative group, indeed we arbitrarily consider indistinct elements from the constant field. To be able to consider the pairwise distinct rational places. And again, P0 and P infinity denote the zero and the pole divisor of the transcendental X. And for the divisor G, recall that we consider a polynomial of degree T. Here degree is at most n minus 1. And this polynomial does not contain this given alphas as a root. And indeed, if we, for instance, if we consider a degree T polynomial, and if we write its principal divisor, zero, if we denote this zero divisor by G0, and the pole divisor is going to be T times P infinity. And obviously, it has disjoint support. Such a divisor has disjoint support with the support of T. But for G, particularly, we want to consider the functions. They have zeros at P infinity of order at least 1, and the poles are described in terms of the zero divisor of this polynomial. So that means these are the functions from the Riemann space of L of G. In some sense, we decrease the zero orders of these functions at this spatial place P infinity. And with this setting, we defined a Goppa code in terms of the dual of this AG code. This can be also represented as, several textbook, you may also come across these notations. And the Goppa code indeed can be described in terms of the subfield subcode of the dual code of this AG code. And again, to be able to give an estimation for the minimum distance and for the dimension, we just note that first this dual again can be represented in terms of NAG code. Here the divisor H is determined by omega minus G minus T, and here omega denotes the Weyl differential with function y1, and h of x is the product of this x minus alpha x. And indeed, if we write this h explicitly as omega minus G minus T, thanks to this setting, this is going to be derivative of h of x minus 2p infinity minus G minus D, and let me denote this D by DL because this is determined by the places which is described in terms of this set L. And in this case, if we write these equalities, we can write it can be written as A minus G0. Here A is the divisor, the principal divisor h of x plus A minus P infinity. And indeed, thanks to these dual descriptions for BCH and Goppa codes, by using the parameters minimum distance of this AG code, finally we can conclude that their minimum distance in the BCH case is bounded below A plus B plus 2, and in the Goppa case, this is bounded below n minus degree A minus G0. Here A is divisor, which is described in this form. And in the discussion session, we will also consider how we can estimate the minimum distance by using the minimum distance of AG codes and the subfield subcodes. So just a last remark, in the literature you may also come across another description of this structure in terms of what is called the residues, and this is indeed, this structure is explained in chapter 4 in the correspondence between the local components of Weyl differentials. So for the simple dictionary, just it's enough to check a couple of pages of the chapter 4, and I think in chapter 9, just again in 2 pages, it's explained how this description can be given in terms of what's called residues. But in our lecture, particularly we only work with, particularly for the computations, we only work with this structure, and we particularly try to construct this omega, and we try to write h explicitly, and our main purpose in general will be to verify this equality, or whenever we want to work with this dual structure, just to convert it to this one. So thank you for your attention in the all semester, and hope to see you future. Bye-bye.